Okay, so if you've been anywhere near the tech news lately, you've probably heard it right. Quantum is hype.
Oh yeah, that headline gets a lot of clicks.
It really does. It's an easy claim, generates that drama because, well, the big promise always seems 5, maybe 10 years away. Still.
Hmm.
But what if we, set aside that idea of the giant universal quantum supercomputer for a minute? What if we look at what really specific, specialized quantum methods are doing, like right now?
Well, that's exactly what our source material digs into.
Right.
There's this quieter story unfolding.
The quieter truth, they call it.
Yeah, it suggests that even really minimal, pragmatic quantum touches, when you slot them into existing classical systems, well, they're already giving measurable gains that traditional methods just frankly can't replicate.
So that's the core tension we're diving into today, isn't it?
Absolutely. The common view is sort of stuck on that huge mega project, the million-qubit, fault-tolerant dream machine that replaces everything.
Right, the one that's always just around the corner.
Yeah, exactly. But for the engineers and the builders we're actually tracking in these sources, the goalposts have shifted. It's not about replacing everything. It's become about practical engineering.
Practical engineering. Meaning?
Injecting these very specialized quantum abilities right where they make a difference. Areas like optimization, handling uncertainty, and maybe most critically, improving sampling and search techniques.
Okay, let's unpack that then. Forget the dream of, I don't know, running Windows on a quantum chip.
Yeah, forget that for now.
If we accept this practical premise, we need to view quantum computing not as some kind of rival to classical, but as a highly specialized tool. So why is that specialization actually its strength, not a weakness?
Well, because if you look at tech history, specialization is often how breakthroughs happen, right? Trying to compare a quantum computer to, say, your laptop running Word,
Yeah.
you're just going to lose that argument every time.
Apples and oranges.
Completely.
Yeah.
The sources are really clear on this. Quantum is fundamentally specialized.
And the analogy they use, which I think helps a lot, is the GPU, the graphics processing unit.
Oh, absolutely. That's a great analogy. Think back maybe 2 decades ago.
Wow.
Nobody called GPUs hype because they couldn't run payroll faster than a regular CPU.
No, that wasn't the point.
Totally irrelevant. GPUs were game-changing because they absolutely crushed the right kind of workload. First graphics, obviously, and then much later, that massive parallel processing needed for AI and deep learning.
And quantum's doing something similar now.
That's the idea. It's starting to tackle specific, really demanding mathematical tasks in a way nothing else can.
Okay, so we need to define those tasks. What are these specialized primitives where quantum is actually, productive today?
We're talking about tools that offer unique insights, often physical insights. The sources point to a few key areas. One is phase estimation.
Which is useful for?
Complex simulations, think material science, designing new catalysts, that kind of thing. Then there's Hamiltonian simulation.
Right, that sounds fundamental.
It is. It's basically modeling how quantum systems evolve over time. That's like the native language for chemistry and, crucially, drug discovery.
And what about search? Because that's a huge bottleneck in so many big classical problems.
Exactly. So we also have amplitude amplification. Now, simplifying a bit, this is basically a way to boost your chances of finding a specific needle in a giant, messy haystack. A huge unstructured search space.
So it improves the hit rate in certain search routines?
Significantly, yeah. And finally, there are certain optimization primitives. These are designed to help navigate those incredibly vast, complex landscapes of possible solutions you find in optimization problems.
So the real breakthrough here isn't about running everything faster. It's more about unlocking new types of search behavior, new simulation capabilities that were just out of reach before. It's extending capability.
That's a perfect way to put it. It shifts the whole conversation away from just speed, and towards new utility. What can we do now that we couldn't before?
And that new utility, that brings us right to the core idea the sources push. Hybrid beats purist.
Yes.
If quantum systems are specialists, then the smart play is to use the classical computing power we already have, but inject these little quantum touches, tiny doses of quantum processing right at the critical points, the bottlenecks.
And this is really where we see the most, let's say, bankable results today. The sources give this really compelling example from drug discovery. They call it quantum QRE.
Quantum QRNG, okay.
Now, they're not running some impossible full quantum simulation of a drug interacting with a body. It's much more surgical. They're using QRNG, quantum random number generation.
Okay, why is true randomness so important there? Aren't the pseudo-random numbers we get from classical computers, PRNGs, usually good enough?
They're good for many things, absolutely.
Well,
But they are fundamentally deterministic, right?
Uh-huh.
They start with a seed and then follow a complex but ultimately predictable mathematical pattern.
yeah.
There's a hidden periodicity. So when you're running these massive simulations like Monte Carlo methods or trying out millions of ways a drug molecule might dock with a protein, like fitting keys into locks, that hidden pattern in the randomness can create, well, silent biases.
Meme.
Meaning the classical system might systematically avoid exploring certain types of solutions. The sources call these rare basins.
And those rare basins might hold the good stuff.
Exactly. They often hold the non-obvious drug candidates. So, by injecting true quantum entropy, genuinely unpredictable randomness from QRNG, they force the search to diversify, to systematically poke around in these neglected corners of the solution space.
Ah, I see. So the value isn't some magic kind of cure. It's finding better candidates that the standard approach might have just missed because of its own built-in hidden patterns.
Precisely. You find candidates the PRNG-driven loop would literally never stumble upon.
Oh, I can definitely see the advantage there. You're basically improving the quality of the candidates. You then feed into the really expensive classical supercomputing part of the process.
You got it.
But let me push back slightly, because this comes up a lot. If the quantum bit is just providing a better, more random seed, couldn't a massive classical system, if you just ran it for long enough with enough different starting seeds, eventually find that same diversity, just by brute force?
That's a fair question.
Yeah.
And theoretically, maybe.
Yeah.
But the key word there is eventually. The time it would take for a classical system to truly randomly stumble into some of those really hard-to-reach basins, it scales terribly.
It could take forever.
Practically forever, yeah.
Yeah.
True entropy doesn't just add more throws of the dice. It fundamentally changes how you explore the possibility space. It alters the search topology itself.
Okay.
The source material contrasts this really well with another example they call quantum tornado, used in severe weather modeling.
Quantum tornado sounds dramatic. Tell us about that, because uncertainty modeling seems like a perfect fit.
It really is. So meteorologists use these things called stochastic ensembles. Basically, they run dozens, sometimes hundreds, of classical weather simulations, each with slightly different starting conditions.
Right, to get a range of possibilities.
Exactly. Now, when they inject quantum entropy into setting up those initial variations in the ensemble, it actually changes how the system explores the really extreme possibilities. Things like atmospheric collapse zones or vorticity paths that can lead to severe events.
How does it change it?
Well, a purely classical ensemble often tends to cluster. It finds a comfortable lane of probability, mostly exploring variations around the most likely outcome.
But the quantum-seeded runs, they break out of that lane.
That's what they're seeing.
Yeah.
They seem to fan out more effectively into the tail scenarios, those low probability but potentially high impact events, the kind of unexpected developments that sometimes precede real disasters.
So it gives you an earlier warning signal for the really bad stuff.
Potentially, yes. An actionable signal under deep uncertainty, maybe further out. It's not about predicting the weather perfectly in the next hour. It's about getting a more accurate picture of the full distribution of risks over the next week or so.
Interesting. So again, it's these small, well-placed quantum touches, reshaping the distribution of possibilities you explore, not replacing the whole weather model.
Exactly. It's about making the classical tools work smarter by feeding them better diversity.
Okay, so if specialization and these hybrid systems are delivering some results, we have to tackle the big critique, the one that always comes up and seems to derail the conversation, the basic physics complaint.
Ah, yes, the measurement problem.
Right. The skeptic says, hang on, the moment you measure a quantum state, it collapses. You only get one classical answer out. So how can you get any real utility if you instantly destroy the very quantum weirdness you're trying to use?
Look, the sources absolutely confirm that critique is physically real. Measurement does collapse the state. But, they argue, modern quantum algorithm design already accounts for this. It's baked in.
How so? They're not trying to pull one perfect number out of a quantum hat.
No, not usually. They've shifted to what the sources call a distribution-first approach.
What does distribution first mean in practice?
It means you don't rely on a single run. You repeat the process many times. You use different quantum seeds, maybe different parameters like annealing conditions if you're using an annealer.
But you build up statistics.
Exactly. You elevate the ensemble over the single shot. Think about it. Complex decisions, whether it's designing a drug or forecasting a flood, they're almost always about managing probabilities distributions, not finding one single magic number.
Okay.
So the state collapse isn't really a bug in this view. It's the mechanism by which the quantum process generates a sample. And the key is that the distribution of samples you get from many collapses can be inherently different, potentially richer, or exploring different areas than what a purely classical sampling method would give you.
But why is the distribution from a quantum seed fundamentally different? If I just run a classical simulation, say, 1,000,000 times with different classical seeds, won't I eventually get a good distribution too? Won't they converge?
They would converge, yes, but potentially to a biased distribution, like we talked about with PRNGs, or one that's stuck exploring only certain regions well. A classical simulation follows its deterministic rules. It explores locally within the landscape defined by the algorithm.
Okay.
Quantum effects, though, especially things like annealing or leveraging true entropy, they can introduce mechanisms that are more like, well, global jumps or tunneling. They can allow the system to escape those deep valleys, those local minima in the solution landscape that might look good, but aren't the best overall solution.
Ah, so they get unstuck more easily.
That seems to be the crucial difference, yes. Quantum-aware systems explore the possibility landscape differently, potentially finding paths or solutions classical search gets trapped away from. It's not just about doing it more times.
That helps answer that other common skeptical question then. Okay, fine, but where are the killer algorithms? It sounds like the sources are saying we don't need one single mythical quantum search algorithm to rule them all. We already have useful ingredients, like tools in a toolbox.
Precisely. Steel tools is a term sometimes used. Productive ingredients. We mentioned amplitude amplification that helps improve search hit rates in certain contexts.
Right.
But crucially, we also have quantum annealing and related variational heuristics. These are the tools that really seem to shine in helping systems escape those local minima traps in really complex, gnarly optimization landscapes.
Gnarly landscapes like protein folding or logistics.
Exactly. Problems where classical search algorithms climb the nearest hill and then get stuck, even if there's a much higher mountain somewhere else hidden behind a valley. Quantum approaches seem better able to sometimes effectively tunnel through or jump over those barriers to find better global solutions, potentially faster.
And what about the chemistry applications? We often hear that, okay, maybe there are speedups, but they aren't generic across all chemical problems.
And the sources agree with that nuance.
Yeah.
Blanket claims of exponential advantage across all of quantum chemistry or material science. That's not really supported by the evidence yet.
So what's the pragmatic approach there?
It's about narrowing the target. Instead of trying to simulate an entire huge molecule perfectly with quantum, maybe you zero in on specific parts or specific types of interactions where quantum effects like electron correlation or symmetry are particularly strong and hard for classical methods.
So quantum acts more like a strategic scout in that case.
That's a great way to think about it. You use the quantum method as a highly optimized scout to figure out which regions of the problem are most promising, or perhaps to calculate a particularly tricky interaction energy.
And then classical computing takes over for the rest.
Yeah, classical HPC does the heavy lifting where it's still more efficient. It's about intelligent resource allocation, using the right tool for the right part of the job.
Okay, let's shift to measurable progress then. How do we actually know these small quantum touches are having a real impact today? What are the builders actually delivering that shows, measured progress beats those maximal promises?
Well, what they're delivering consistently now are these traceable, entropy-aware ensembles, meaning every simulation run, whether it's used a standard classical PRNG seed or a QRNG seed, or maybe parameters from a quantum annealer, is logged. The source of the randomness or the heuristic is tagged, the outcome is recorded, and critically, it's reproducible.
So you can compare apples to apples, or rather QRNG apples to PRNG apples.
Exactly. And they can demonstrate a quantifiable difference. They can show increased diversity in the solutions found, or wider, earlier exploration of those risk paths in weather modeling, or those potential drug confirmations. It's becoming empirical.
And tied into that traceability is this fascinating idea the sources mention about auditability, which is crucial, right? If you're dealing with high-stakes stuff like designing drugs or modeling floods, you can't just say, our quantum magic box found a better answer. You need to prove how the search was done, where the result came from.
Absolutely vital. And the sources detail this emerging system for essentially symbolic encoding and creating audit trails. Because you're running these quantum-seeded ensembles potentially hundreds or thousands of times, you need a way to categorize and compare the results efficiently.
So what did they develop?
They developed a kind of symbolic compression. Think of it almost like a linguistic layer, using these things called Zaban glyphs currently.
Zaban glyphs, okay.
Yeah, it's a way to tag and compare the patterns of collapse outcomes across different runs. It creates a compact signature for the kind of distribution each run explored. This helps them triage results, prioritize interesting findings, and crucially, trace it all back to the specific quantum seed or annealing parameters used.
Wow, okay. So this symbolic encoding, these glyphs, they create a kind of auditable fingerprint for the quantum part of the process?
That's the idea. It makes the science traceable. It proves the origin was this PRNG, QRNG, or annealer seeded. What were the parameters? It addresses that need for provenance. You can't really claim an advantage if you can't transparently show your method, and this helps ensure that.
Okay, let's try to pull this all together. If we synthesize everything, what's the real bankable quantum advantage that practitioners can actually leverage right now? What are maybe the 4 key takeaways for someone thinking about using this tech?
Okay, 4 takeaways based on the sources. First, search diversity. Using true randomness like QRNG helps eliminate those silent biases you get from classical pseudo-randomness.
Right, explore more widely.
Second, optimization escapes. Using quantum annealing or variational heuristics gives you a better chance of jumping out of those suboptimal local minima that trap classical search algorithms.
Find better solutions in complex landscapes.
Third, uncertainty workflows. Shifting your mindset towards generating and analyzing ensembles of possibilities, thinking distribution first, rather than chasing a single perfect prediction.
Manage risk better.
And fourth, auditability. Leveraging these new symbolic encoding methods like those Zaban glyphs to track the provenance of your runs and make the whole process transparent and reproducible.
Prove your work. Okay, those are concrete. They aren't flashy headlines, are they? They're incremental, practical gains from smart engineering.
Exactly. And maybe that's the message for the skeptics too. Look, healthy skepticism is always vital in science and engineering. But lazy cynicism, just repeating its hype, misses this quieter, steadier movement forward.
Yeah.
Progress nearly always arrives where it's most useful first, often integrated into hybrid tools, not as some sudden revolution. We saw that with GPUs, we saw it with AI accelerators, and quantum integration seems to be following a very similar pattern.
So we've kind of moved past the need for miracle headlines and focused instead on how to get better coverage of the unknowns, the uncertainties, the complex spaces that really matter in practice. And the advantage, it seems, is being banked today by the people focused more on discovery and practical results, not necessarily on, theatrical presentations.
I think that's fair. Remember, the catchy slogan that gets clicks is, "Quantum is hype." But the engineering approach that seems to be making actual progress is more like, quantum is a tool, use it intelligently, where it genuinely changes the nature of your search or simulation.
So a final thought for our listeners.
Yeah, maybe think about your own field. Look at the really tough combinatorial problems you face, or the high-risk modeling, or the complex searches, and just ask, where could an ensemble-first approach or a distribution-first mindset benefit from a little targeted injection of diversity, or maybe a better way to escape those optimization traps? It might be more applicable than you think.
Not hype, just results. That's been our deep dive into minimal quantum, perhaps. Use the maximal way.